All right, if we put together those laws, we come up with what we call the combined gas law. We know that Boyle's law said that pressure and volume differ inversely. We know that Charles' law said volume and temperature vary directly. Okay, so since that temperature varies directly, we can put it under there. And then Gay-Lussac said that temperature and pressure vary directly, so that relationship is also there. So we can put all three gas laws together like this. Now, one way to help you remember this relationship, if you think about, and the laws that they go with, we're going to go write out good travelers check passports before traveling. All right. Now, the first one, good. Gay-Lussac starts with G. Vacationers, not travelers. Okay, good vacationers. So, if I'm a good vacationer, if I take out the V, isn't that Gay-Lussac's law? P over T, right? Check passports. All right, I guess I can't just erase it. I'll do that. Check passports. So now I'm going to, Charles' law, we're going to cover up the P for passport. Oops. And we get volume over temperature. That's Charles' law, volume over temperature. Good vacationers, for Gay-Lussac, you don't consider volume. Check passports. For Charles, we don't consider pressure. Before traveling, for Boyle's, we don't consider temperature. Okay, so that's one way that you can remember. If you can remember PV over T, that's one more way that you can remember which law is which. All right, so all we have to do, again, is just plug and chug. We have a 888 millimeter balloon. That's our volume. Here's temperature 1. Of course, we have to change it to Kelvin. 14 plus 273. 287. And here's pressure 1. The temperature is raised, so 56 plus 273. This is T2. The pressure's dropped to 70. It's asking for volume 2. So I'm going to write them over here so I have a little bit more space. P1 is 93.3 times T1, or P1 times V1, 888 milliliters, divided by T1, which was 287 Kelvin, is equal to P2, 70 atmospheres, times V2, which is what we're solving for, divided by T2, 329. Now, we just do the multiplication. So if we take 93.3 times 888 divided by 287, we get 288.7 is equal to 70 divided by 329 V, 0.213 V. Now we solve for V. And our second volume is going to be not the right answer. Let me try this again. 93.3 times 888 divided by 287, 288.7. 70 divided by 329 is 0.212. So 288.7 divided by 0.213. Okay, I guess that is right. So we get 1,355 milliliters. Let's try the next one. Here is V1, T1, P1, V2, and T2. So we have pressure 1, pressure 1 is 99.7. Volume 1 was 3.04. And temperature 1 is 17 plus 273, 290. Pressure 2 is what we're solving for. Volume 2 is 3.25 liters, and temperature 2, 35 plus 273 is 308. So pressure 2 is going to equal 99, and our units we were using were atmospheres. All right. Avogadro's law, we're going to throw in the number of particles now. And Avogadro's law says that there's a direct relationship between the number of particles and pressure. No. Equal volumes of gases at constant temperature and pressure have equal numbers of volumes of particles. So there's a direct relationship between number of particles and the volume. That's what I'm looking for. So because we have volume on top, we're going to put number of particles on the bottom. Now this makes total sense. If you blow up a balloon, you're putting more particles into the balloon. The balloon's going to get bigger. Okay? Total sense. Now, when we put these all together, we end up with P1V1 over N1 and T1 is equal to P2V2 over N2 times T2. Now, if you're not changing the number of particles, it's a closed container, you don't have to worry about number of particles. But what if you are? Okay? It's always a good idea to have something to compare it to. So if we want, let's say we want to figure out a constant, something that we can compare, and we can call that the ideal gas constant. And the way we get that, first of all, we have to define standard temperature and pressure. Standard temperature and pressure, STP, standard temperature is 273 Kelvin. Standard pressure is 1 atmosphere. It's defined as the atmosphere at sea level, which would be 760 millimeters of mercury, which would be 101.3 kilopascals. Okay, we're going to use the atmospheres most of the time. All right, so if we know at standard temperature, we're going to put 273 in here. And at standard pressure, we're going to put 1 atm. And we know we have 1 mole, so I'm going to put 1 mole in here. Here's where Avogadro comes in. Avogadro figured out that at standard temperature and pressure, if you have the same temperature and pressure of a gas, it will compare, one gas to another will compare, they'll have the same volume. So everything else is the same. The volume, even if they have different masses, the volume will be the same. Okay? If we take 1 liter of gas, or if we take gas and we have 1 mole of that gas, 1 mole of that gas at 1 atmosphere and 273 Kelvin has a volume of 22.4 liters. Now we need to get our mole maps out. All right, now we need to pull out the mole map because we need to do the last corner. And I think I had you guys, when we did notes on moles, fill this in, but that was in the notes, and if you've got still have your cardstock one, or if you just want to make a new one, this is the last bit of the mole map. The relationship between moles. If you have a gas, if you have 1 mole of gas at 0 degrees Celsius, 273 Kelvin, and 1 atmosphere pressure, it will take up 22.4 liters. So this is volume of a gas. 1 mole will take up 22.4 liters per mole. So if you're going to go, I have to make sure I do the conversion right. 1 liter, 22.4 liters in 1 mole. So 1 mole times 22.4 liters per mole. So you're going to multiply this times 22.4 liters per mole and divide by 22.4 liters per mole. Okay, this is called the molar volume of a gas. So that is where we come up with 22.4 liters. All right, so what I'm doing is I'm going to put that volume back up here. If you do the math for that, you come up with what we call the ideal gas constant, which they use R, don't know why, and it equals 0.0, make sure I say it right, 0.0821. Here's the relationship down here. All right, this is what we just talked about. I'm going to plug in 1 atmosphere, 22.4 liters, 1 mole, 273 Kelvin. And if I do that, I come up with 0.0821. And the units are very freaky, liter atmospheres over mole kelvins. That is equal to P1 V1 over N1 T1. P1, right, which is right here. P1 V1 over N1 T1 is equal to that constant. If we rearrange that, we get PV equals nRT, which some people like to say perv nerd. This is the ideal gas law. The ideal gas law, PV equals nRT, we can use to solve anything that has moles in it that we need to. Okay? R is either going to be, if we're talking about atmospheres, 0.0821. If we're talking about kilopascals, R is 8.31 liter kilopascals over mole kelvins. If we're talking about millimeters of mercury, it's 62.4 liter times millimeters of mercury over moles degree Kelvin. And it's not really degree Kelvin, it's just mole kelvins. So we're going to use atmospheres. That's the one that you need to worry about. There may be some that you have to do conversions on the online stuff, but I've got worksheets that you can practice with that will only use atmospheres. Okay, so let's practice a couple. I have 4 moles of a gas. 4 moles is our value for N. P is our pressure. Volume is 12. We're going to solve for temperature. So we're going to use PV equals nRT. 5.6 atmospheres times 12 liters is equal to 4.0 moles times R, which is 0.0821 liter atmospheres over mole Kelvin. And that will all cancel out if you care about it. If you don't, and take my word for it. And we're going to solve for temperature. How do I get T by itself? I'm going to move this. Nope. That's not what I wanted to do. Move this. And it didn't work. I'm going to move this over here. Now, we'll solve for T. I'm going to divide both sides by 4.0 moles times 0.0821 liter atmospheres over mole Kelvin. That cancels, that cancels. Now we have to take that. I'll do the math for you. So 4 times 0.0821 is 0.3284, and we've canceled out our moles there, so we have liters atmospheres over Kelvin, and that's going to equal temperature. So 5.6 times 12 divided by 0.3284 gives us 204.6 Kelvin. Okay. Next one. I have an unknown quantity. N is what my unknown is. My pressure is 1.2. My volume is 31 liters. And my temperature is 87. 87 plus 273 is 360 Kelvin. Plug and chug. PV 1.2 atmospheres times 31 liters is equal to N, which was unknown this time, and T is 360. I'm going to erase that so I can write in there. Okay, solve for N. So we're going to divide both sides . 1.2 times 31 divided by 0.0821 divided by 360. We get 1.258, so we'll go 1.26 moles. Okay? Number 3, if I contain 3 moles of gas in a container, so I've got, this is N. I'm going to erase this so we can see. Here's V, here's T. We're going to solve for pressure. PV equals nRT. So P is our unknown. 60 liters is equal to 3.0 moles times R, 0.0821 liter atmospheres over mole Kelvin times 400 Kelvin. We're going to divide both sides by 60. And our pressure is going to be 1.64 atm. Next one, we're going to solve for volume. So here is our number of moles, here is our pressure, here is our temperature, 56 plus 273, 329. What is the volume of the container? So we have 0.090 atm times volume is equal to 7.7 moles times 0.0821 liter atmosphere over mole Kelvin times volume or temperature, which is 329. So 329 times 0.0821 times 7.7 divided by 0.090, 311 liters, if I did the math right, which is always subject to question. All right, we're going to stop there. My recommendation, I went ahead and added, no I didn't, I added them here. My recommendation is you go ahead and work through this page, these two pages that I've uploaded on Classroom. We've got combined gas law, we've got Gay-Lussac, we've got Charles, we've got Boyle's, and we've got some conversion factors up at the top. If you want to do that instead of the online stuff, that's fine with me. The online stuff's not loading, so I will take a picture of it and upload it for you so you can see what you need to do.